Welcome! This is the next in the series of videos I've been producing about understanding space weather. In the last video we saw how differential rotation of the Sun both generated and strengthened magnetic fields. One of the major consequences of that process is the appearance of sunspots on the surface of the Sun. Well, how cool are sunspots? Well, let's compare them with the surface of the Sun. The surface of the Sun, the photosphere, is at about 5700 degrees Kelvin, whereas sunspots are nearly 1000 degrees Kelvin cooler. Remember, that is still hot enough to melt tungsten, which is the element with the highest melting point. But because they're cooler, sunspots emit less light and at slightly longer wavelengths. So they appear dark by contrast compared to the surface of the Sun. Now, to give you some idea of how bright they really are, if we were able to pick even a small sunspot off the surface of the Sun and put it up in the sky, it would be many times brighter than the full moon. Sunspots come in all sorts of sizes. The smallest sunspots we can see are called micropores, and they are barely detectable from Earth. They're about 200 kilometers across or less. The largest sunspots can be as big as Jupiter, 140,000 kilometers across. So we have a dynamic range in the size of sunspots of about 1,000. However, the Sun is puny compared with other stars. Some stars have star spots that cover a large proportion of the surface of the star, and in fact can be many times the size of the Sun. Some of you may have some of those eclipse glasses left over from the eclipse last month. Don't throw them away, they might be useful. Some sunspots get so large they are visible to the naked eye. Now, you should never look at the Sun directly or through any form of optical instrument that doesn't have a full aperture solar filter on it. But if you hear that there are major sunspots on the Sun, or there's a lot of solar activity going on, get out those old solar eclipse glasses, put them on and take a look at the Sun. You may be able to see the sunspots directly. In fact, you will see spots before your eyes. We said earlier that sunspots were cooler. We didn't explain why sunspots are cooler. They are cooler because they are magnetic. Well, how do we know they're magnetic? Well, there's an effect in physics called the Zeeman effect. So in the presence of a magnetic field, some spectral lines split into three components. So you can put the slit of a spectrum across a sunspot and look at one of those lines and see if it splits, and it does. And the amount it splits tells you how strong the magnetic field is. So not only can you tell that it's magnetic, but you can tell how strong the magnetic field is. And we find that sunspots have very, very strong magnetic fields, probably 20,000 times stronger than that of the Earth. Now, that strong magnetic field inhibits the flow of energy from below. That means that the sunspots emit less energy, so they are cooler and therefore appear darker. You can use the Zeeman effect to map the solar magnetic field. Such pictures are called magnetograms. On the left here we have a picture of the Sun taken in ordinary white light showing the sunspots. On the right we have a magnetogram which shows the magnetic field. You can see not only the strength of the magnetic field, you can also see the polarity, dark being negative, i.e. magnetic field that's going away from us, and white being positive, which is magnetic field coming towards us. Now, you'll note that there are areas where there is magnetic field and only very weak spots, and even some areas where there is magnetic field but no spots. So there seems to be some sort of threshold required to be able to produce a sunspot. Sunspots are very complicated structures when you look at them in detail. You can see the surface of the Sun, the photosphere, and all the convection cells called granulation. Now, the sunspots are superimposed upon that. In the dark center of the sunspot, where the fields are vertical and very strong, that is called the umbra. Around the umbra there's generally a penumbra or weaker zone with more horizontal magnetic fields. And then finally, as we heard before, there are the small sunspots that tend to surround these larger spots called pores. They tend not to have a penumbra. Sunspot groups can come in all sorts of shapes, and one of the ways to distinguish between them is to create a classification system. One classification that was historically used assigns 3 letters to a sunspot group, which determine the shape of the region, the size of the sunspots, and the distribution of spots within that region. Now, I don't find this particularly useful, so I much prefer to use the magnetic classification system. Here's a single spot, so this would be called an alpha spot, and if you look at the magnetic field, it would be all one polarity. Now you notice it's surrounded by some dark and light areas, that's in the photosphere, and some of these areas seem to be forming hexagonal-like structures. That's called supergranulation, and implies that there's a larger scale of convection within the convective zone than just the granulation itself. Now that has nothing to do with sunspots, I just thought you might be interested in that. Now a beta region has two polarities in it and may have multiple spots. A gamma region is the same sort of thing but much more complicated. It may have many different spots and spots that are moving around. And the last classification is a delta classification, which says there are mixed polarities within the same penumbra. So when you see a region classified magnetically as beta gamma delta, it says that big flares are very likely. Sunspots are dynamic. They emerge from beneath the surface of the photosphere. They move around. They bump into each other. They can rotate. And they can decay away. Each one of these dynamical processes can result in major solar activity. Let's take a look at the emergence and evolution of a sunspot region. So in summary, we have learned that sunspots are transient features on the surface of the Sun. They're made up of strong magnetic fields, which inhibits the flow of energy from below and makes them cooler, so that's why they appear darker than the surrounding photosphere. The larger and more dynamic events cause big flares. In the next video, we'll be dealing with the solar cycle. Until then, stay safe.